Hey everybody, it's Miss Berry. In today's video, we're going over section 3.4, which is called Measures of Dispersion. In this video, we are going to be talking about how a data set that is more spread out can affect some of the sample statistics that we calculate or the population parameters of that data set. So I'm going to go ahead and flip my camera around and share my screen with you guys, and we'll get started. This video is going to be recorded in the same way as the section 3.1 video was, so I'll have sort of like a split screen where you can see the PowerPoint as well as my calculator. All right, so let's get started. Right, get everything on here. All right, we're just going to start off looking at the PowerPoint for a minute and move that out of the way. From beginning, swap. Okay, perfect. All right, so we are looking at section 3.2, which is called Measures of Dispersion. Dispersion refers to how the data set is spread out. All right, so by dispersion here, what we mean is spread out. Let's see if I can write on here. Nope. All right, so let's talk about our three measures of dispersion. And I'm referring to three here. There are really more than three. You could also look at something called the interquartile range, which we'll talk about in the next video. But these are three measures of dispersion that are commonly calculated when you're working with a data set. The first and the easiest to calculate is called the range. The range just has a little formula that it uses. So let's see if we can write it. I think it's going to let me now. Okay. It's just equal to the maximum value in your data set minus the minimum value in your data set. Very quick and easy to calculate. All right, so the range is the difference between the highest and the lowest values in the data set. This is helpful for us because it gives us a quick sense of how spread out the data are. All right, so whenever we, the other day in the last video, whenever we calculated one variable statistics, it's not going to just spit out the range in the output, but it will tell you the maximum and the minimum. So you just have to plug those two numbers into this formula. All right, now getting into the variance and the standard deviation, these are more complicated to calculate. They have pretty complicated looking formulas. You can look those up. They're in your textbook or in the Learn section on Hawks if you want to watch that, or if you want to look at that. Look that up in your textbook or Google it. I'm not showing you the formulas here because I'm not going to be asking you to manually calculate the variance and the standard deviation. We're going to use our calculator to find those statistics. So I'm not giving you the formula here. I'm just giving you a description of the measure. All right, so the variance measures how much the values in the data set differ from the mean of the data set. The larger the variance, the more spread out the data points are from the mean. All right, so what you would like to have, ideally, is you would like to have a small variance. You would like for all of your data to sort of be clustered together, and that way it's going to show a trend in your data set. But the more spread out the values in your data set are, the higher the variance is going to be. All right, and then from the variance, we can calculate what we call the standard deviation, and it's just the square root of the variance. All right, so let me just write couple little algebra things here to show you the relationship. All right, so the variance is equal to the standard deviation squared. So the variance is equal to the standard deviation squared, or you can think of it as the standard deviation is equal to the square root of the variance. These are two versions of the same formula. They're just algebraic rearrangements of the same formula. All right, so the standard deviation is the square root of the variance. It's going to provide a measure of the average distance that each point is from the that each data point is from the mean. So if the standard deviation is 2, you would say, okay, well, in general, every data point in our data set is 2 units away from the mean. The unit is going to depend on what your data set is. If we're dealing with heights, which we're going to be looking at in a minute, then you might say on average, every student is about 2 inches either taller or shorter than the average height. All right, so again, the larger the standard deviation, the more spread out your data set is. You're going to see people use the standard deviation more frequently, and that's because whenever you take the square root of the variance, it puts your standard deviation into the same units as the data set itself. So it just makes the standard deviation a little bit easier for us to interpret. All right, so whenever we calculate, whenever we start doing our inferential statistics, you're going to see that most of the time I'm going to be giving you the standard deviation of the data set as opposed to the variance. All right, so the last thing I need to tell you before we can get into the calculations is the formula, or excuse me, not the formula, the symbol. My goodness, sorry. All right, so the symbols, these are important. Make sure that you get these down. You're going to see these symbols over and over. So if you don't memorize these, it's going to be difficult for you. So you're going to have to constantly refer back to your little formula sheet that shows you what all the symbols are for each of the statistics. So, or the parameters. So make sure that you get these memorized. All right. So just like before, with the mean, we saw that the population was represented with a Greek letter. So the symbol for the population is going to be a Greek letter. Whereas for the sample, we're going to be just using letters from our regular old Latin alphabet. All right, so the symbol for the population variance is sigma squared. This is the Greek letter sigma. All right, so Greek letter sigma. So we would read that as sigma squared. All right, we saw before that the standard deviation is just the square root of the variance. So if you take the square root of the sigma squared, it's going to cancel out. The square root is going to cancel out the squared. So you're just going to be left with sigma for the standard deviation. All right, so just sigma for the standard deviation. All right, and again, this is for the population. For the sample, we're going to use our corresponding, our corresponding letter from our Latin or Roman alphabet. The variance is going to be S squared, and the standard deviation is going to be S. Okay. Make sure you get those symbols down. All right, so here we have arrived at the calculation portion. All right, so we're going to use our calculator to find the range, the sample variance, and the sample standard deviation of the following data set. All right, so the word sample here is important because whenever you look at your output from your calculator, you're going to need to know if you're working with the entire population or if you're just working with a sample of the population. So this is just some random sample that I took of the heights of my students. All right, so this is just a sample. This is not representative of all of my statistics students. So we're going to be calculating those sample statistics as opposed to the population parameters. All right, so let's get this little split screen. Oops. Yes, okay, so let's get this little split screen going here and start typing this in. All right, so just like in our last video, you are going to start by going to Stat. So go to the Stat button. All right, so you're going to hit your Stat button right here. Then you're going to go to Edit, option number 1, which is Edit. And then you're going to type the data into the L1 column. Everything's going into the L1 column. Okay, so we're going over here. You might have this typed in from our last video. If you do, you can skip ahead a little bit in the video. If you have not typed it in, you might want to pause the video. And that way you're not rushing trying to type all this in. Because remember, if you type in even one of these wrong, it's going to make your answers wrong. All right, so take your time. It's worth taking the extra couple of minutes to type this in carefully, whether you're working on the homework or on the test. All right, I typed that in really fast just to show you how easy it was. See, I totally messed this one up without even noticing. All right, so 73, that's supposed to be 64, 77, 60. All right, I'm just scrolling back through. I'm going to go to the top, scroll back through, make sure everything looks correct. Okay. Everything looks right. All right, so now that I have typed my data in, I'm going to go back to Stat. All right, so I'm going back to Stat. This time I'm going to use my arrow to go over to Calc. All right, so I'm going to go back to Stat, and this time I'm going over to Calc. And once again, just like the other day, I'm choosing option 1, which says 1 var stats. That means 1 variable statistics. All right, so 1 variable statistics, hit enter, and you're going to want list to say L1, and frequency list should be blank. And just like we talked about the other day, based on what type of calculator you have, whether you have a TI-83 or TI-84 plus, yours may your screen here may look slightly different than mine, and that's okay. All right, so I'm going to go down to calculate and hit enter, and there are my statistics. All right, so you can scroll up and down, see all of the output. All right, so just like the other day, we saw that the mean is 66.7. I'm supposed to be calculating the range and the sample variance and the sample standard deviation. All right, so for the range, we're going to need the maximum and the minimum, which is at the very bottom of your output. All right, so our range, remember that was equal to the maximum minus the minimum. All right, the maximum minus the minimum, that's going to be, looking at my output here, 77 minus 60. It told me my max was 77 and my min was 60. All right, so that's 17. All right, so the interpretation here would be that the range is telling me that from the largest value to the smallest value it's spread out 17 inches. Remember, this is the heights in inches. All right, then the next thing we're supposed to calculate is the sample variance. Remember, that's S squared. All right, so let's look through our output. We're at the very bottom, so I couldn't go any further. I can see SX up there at the very top. I'm going to scroll up a little bit. There we go. SX, that is the standard deviation. All right, so S, remember S is the standard deviation. So S is 2 decimal places. That would be 4.65. All All right, so again, if you're looking at the standard deviation, it's in the same units as the original data set, so this would be inches. So we would say on average, a data point is about 4.65 inches away from the mean, whether it's taller than the mean or shorter than the mean. Right. In order for me to get the variance, the sample variance, I just need to take that standard deviation and square it. So 6.4, whoa, said that backwards, 4.65 and then square it. So let's come over here and do that. You can see when I start typing it takes my output away. 4.65 squared, gosh, apparently that's hard for me to say, is 21.62. 21.62. A little bit harder to interpret since it's not in the same units as our data set any longer. But we can just say that the higher that variance is, we know the more spread out our data set is. 4.65 is pretty small for a standard deviation. That's a pretty good standard deviation. You could have, I've had data sets with much larger standard deviation. So this is a pretty good standard deviation for what we have going on here. All right, so hopefully that seeing that process helps you whenever you're calculating the standard deviation and the variance and the range on the homework. For the rest of the video, we're going to be doing some interpretations as well as looking at the empirical rule. So we're going to jump back over to our PowerPoint and finish that stuff. All right. All right, so interpreting standard deviation. So using the data from my classes from a previous semester, I calculated the following standard deviations of the heights of my students. So I was teaching statistics at 9:30, and then I taught it again at 11 a.m. For the 9:30 class, their standard deviation of their heights was 3.22 inches. And for the 11 a.m. class, the standard deviation of their heights was 4.76 inches. And the question is, how do we interpret this? What do these two standard deviations tell us about the heights of the students in these classes? And then down here, I have a little interpretation for you. The higher the standard deviation, the more spread out the data set is. So that tells us that the heights of the students in my 11 a.m. class were more spread out than the heights of the students in my 9:30 a.m. class. So if I'm picturing this in my mind, I'm picturing that the heights, let's say this is like height um, on my vertical axis, maybe like, what do we say? My minimum was 60 inches. Let's do like 65, 70, 75. I think the maximum was 77. So we'll go to 80. All right. So you can imagine that all of my, for my 9:30 class, all the heights were sort of more closely clustered together. All right. So they're all sort of clustered pretty closely together. Whereas for my 11 a.m. class, they were a little bit more spread out. So maybe we had some really tall people in that class, or maybe we had some really short people in that class. All right. So their heights were just a little bit more spread out, less clustered together. So this was the 9:30. Here's the 11 o'clock. All right. So if I'm picturing this in my mind, I'm just picturing for the smaller standard deviation, the heights are more clustered together, whereas for the larger standard deviation, the heights are more spread out. All right. Building on what we've just learned about the standard deviation, we can talk about the empirical rule. This is a pretty good graphic. I want to say I pulled this out of your textbook for the empirical rule. So what you see here is what I would like you to imagine in your mind is that this is a smooth curve that's been drawn on top of a histogram. All right, so underneath here are a bunch of little bars for my histogram. All right, so that's what I'm wanting you to imagine is happening here. All right, so there's a bunch of little bars under there. And then what I've just done here is drawn a smooth curve over all of those bars. And that's what we're looking at. Okay, so this is called a normal curve. All right, so a normal curve. Right, a normal curve is, I want to say we talked about this back in like section 2.3 maybe. But a normal curve is a special type of symmetrical distribution where the peak is in the middle. All right, so the empirical rule gives us a breakdown of how we expect the data values to be clustered, or sorry, our data points to be clustered. We expect, let me switch to my laser pointer. We expect most of the data points to be right here in the middle, right? So that's where the peak is, that's where the mode is, that's the value that occurs most frequently. This is where the average is in a normal distribution. So we're expecting that most of our data points are right here in the little middle chunk. And then as we go out, so imagine we're talking about heights here, right dead center, you've got the average height. Right, so I'm going to write X bar, right? You could also do mu for the population mean. X bar or mu, that's dead center. Whether you're dealing with the population or the sample would determine whether you're using X bar or mu. All right, I'm going to take away the mu just so it's not confusing. All right, so if I go one standard deviation to the right, so all I got to do is take X bar plus S. So one standard deviation to the right, that's this line right here. If I go one more standard deviation to the right, that would be X bar plus 2 standard deviations. That's an S, not a 5. And then if I go one more standard deviation to the right, that's over here, X bar plus 3 standard deviations. Again, that's an S, looks like a 5, but it's actually an S. Okay. So what the empirical rule says is that as we add these standard deviations, if we're dealing with heights here, as people get taller and taller, you're going to see less of those really, really tall people. Most people are going to be clustered right here in the middle, around 60 inches for my class. So you're going to have a few people that are really tall. And then on the opposite end, you're going to have a few people that are really short, right? So you're going to have a few really tall people, a few really short people. Most of us are falling right here in the middle. All right, and that's really all the empirical rule is saying. I know it looks complicated, but all it's saying is giving us specific percentages for how many of our data values we can expect to see in that portion of the normal curve. All right, so I'm just filling in how you get these numbers. All right, so each little color change here refers to a standard deviation that's being either added or subtracted. If you're going to the right, the standard deviation is being added. If you're going to the left, the standard deviation is being taken away. Now, what the empirical rule is doing is it's giving us specific percentages for what we can expect our data set to look like. So we're expecting 68%. 68%. Where am I getting 68% from? 34 plus 34 is 68. We're expecting 68% to be of the heights, let's say of the heights, to be in between one standard deviation to the left and one standard deviation to the right. If you go out another standard deviation, we're saying, okay, well, within 2 standard deviations, we're expecting about 95% of the data points to be in between 2 standard deviations. All right, so this would be 13.5 plus 34 plus 34 plus 13.5. That adds to 95. All right, and then now we're going to include those really short people and those really tall people. we're getting even smaller. We're saying only about 2.35% of our data set are we expecting to be down here, these really short folks, maybe just one or two in a class. And then same thing over here. Maybe we have one or two really tall people in a class. And if you add up all the percentages, 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35, that all adds to 99.7. Now that's not 100% of the graph, right? We've left out 0.3%. All right, so that's the only hang up that I have with this picture. That's the only part of this picture I don't like, is that it doesn't tell you what's in these little tails over here. All right, so 99.7 is in between three standard deviations. But the 0.3 gets split up between these two tails. So there's 0.15% in the right tail, and there's 0.15% in the left tail, in the lower tail. All right, and then up at the top, I didn't mention this, but we are going to be using it, so I want to bring it to your attention. If you're just saying how many people, or what percentage, I should say, what percentage of people are taller than the mean, it should be 50% of your data set, right? The mean is the halfway point. It's the, in a normal distribution, remember the mean is the same as the median, is the same as the mode. So this is truly representing the halfway point of your data set. All right, so if your data set follows this normal distribution where the peak is in the middle, the mean, the median, the mode, they're all about the same, then we can truly say that half of the people in the class are taller than the mean and half of the people in the class are shorter than the mean. All right, now this is going to come in handy, the 50% at the top. That's going to come in handy. So we are not going to forget that. Okay, so we're going to refer back to that in just a minute. All right, so here are your the official rules that accompany this picture. So it says approximately 68% of the data points are going to lie within one standard deviation of the mean. All right, so we saw that illustrated here in the purple. All right, so approximately 68% of your students are going to have heights that are in the purple area. All right, then next bullet point down, approximately 95% of the data points are going to lie within two standard deviations of the mean. All right, so that's the purple and the green. All right, so you're saying I'm expecting 95% of my students in my class to have heights within two standard deviations of the mean. All right, so most of my class is going to be in either the purple or the green areas. And then as I get out into my tails, I've got less and less people out here. Approximately 99.7% of my data points are going to lie within three standard deviations of the mean. All right, so that should capture almost my entire class. I might have one outlier, one person that's really, really tall or really, really short that's out here in these little tails that are not filled in. Now, the word approximately here is important, and we're going to make that part of our answer each time. All right, so the empirical rule is an approximation. Right, the empirical rule is an approximation, so we have to add that little word in there to make sure that we are not inappropriately interpreting the empirical rule. Sorry if you can hear that weird noise. I think people are moving furniture upstairs. All right, you can see for some reason I've got this one number that has already shown up, but it's okay. We'll just pretend like that's not there. All right, so switch to my little laser. Suppose that the GPAs of students at CCGA have a bell-shaped distribution, also known as a normal curve or normal distribution, with a mean of 2.6, so the average GPA is about 2.6, and the standard deviation is 0.44. Using the empirical rule, what percentage of the students have GPAs that are between 1.28 and 3.92? All right, so the way that I would suggest that you approach this is to just draw the curve. All right, so you can see I've got a really crudely drawn normal curve here. It doesn't have to be perfect, doesn't have to be beautiful, So we've got a little normal curve peak in the middle, and then it's going to get shorter in the tails. All right, so shorter down here in the tails. All right, I'm going to start by labeling my normal curve. I'm going to put the mean in the middle. All right, so you can see I put my mean 2.6 on that middle line. So that's right there, dead center at the peak of the normal curve. And now I'm going to start labeling the rest of my little tick marks. So you can see I've gone 1, 2, 3 to the right, and then 1, 2, 3 to the left. Now, how do I get those numbers? I just add or subtract the standard deviation, whichever one's appropriate. If I'm going to the right, I should be adding the standard deviation. If I'm going to the left, I should be subtracting the standard deviation. All right, so I'm going to show you this the long way for this first one. And then from then on, we'll just do it on our own. All right, so 2.66, sorry, I've done this every time. 2.6 plus 0.44, that's going to give us our first standard deviation to the right. That's 3.04. So boom, 3.04 goes on that first tick mark. Add 0.44 again. Right, that's going to be our second tick mark, 3.48. All right, so there's people with a 3.48 GPA. And then add 0.44 again. That's our third tick mark, 3.92. That's the number we were looking for. Remember, 3.92, that was part of the problem. All right, so we know that's going to be used in some way. But now let's go to the left. All right, we need to get to that 1.28. So let's go to the left. We're going to subtract 0.44 this time. So 2.6 minus 0.44 is 2.16. Let me draw that on here just so I have it written down somewhere. All right, so 2.6 minus 0.44 is 2.16. You can see that next one's already filled in. Minus 0.44 again gives us 1.72. Minus 0.44 again gives us 1.28. All right, so you are just repeatedly either adding or subtracting the standard deviation. So you can see here, I have added it 1, 2, 3 times. And then when I was subtracting, I subtracted 1, 2, 3 times. That gives me each of those little tick marks. All right, now I'm going to bring back my picture. All right, there's my numbers, 1.28 and 3.92. The shade in the area between, because they said how many or what's the percentage of students that have GPAs between those two values. So I shaded in between. All right, and there's our picture. All right, so we are 1, 2, 3 standard deviations out to the left, and we are 1, 2, 3 standard deviations out to the right. So if we go 3 standard deviations to the left and 3 standard deviations to the right, that's that bottom line there. We know that that's 99.7%. Now, this one was super straightforward, very easy. Now, don't forget to include the word approximately, but it can get more complicated than this. Let me show you a very similar problem that would be a little bit more complicated. So let's say that instead of this being 1.28, let's say that was 1.72. Okay. So let's say that was 1.72 instead. All right. Then we would be going from here to here. When you have the same number of standard deviations on each side, it makes it a lot easier. Here's an example where on the left side, we only went out 2 standard deviations, but on the right, we went out 1, 2, 3 standard deviations. So in that case, you're just going to add up each little chunk, okay? So we're going to add up the 13.5, right? That's the first chunk. Let me see if I can write these in here where you can actually see it. All right, so there's the first chunk, 13. Oh, yeah, that didn't work very well. 13 point, I'll write it above it, 13.5. Second chunk, 34%. Third chunk, 34% again. Next chunk, 13.5% again. And then our last little tiny chunk is 2.35%. All right, then you would go to grab your calculator, start adding these up. 13.5 plus 34 plus 34 plus 13.5 plus 2.35. That's 97.35%, approximately. All right, so if it's the same number of standard deviations on each side, you can just use 68, 95, or 97, 99.7 that's designated in the empirical rule. If it's different number of standard deviations on each side of the mean, then you're going to have to manually go through and add up the chunks, add up the little percentages. All right, so let's look at a different example. All right, so you can see I've got my little normal curve on there. Suppose that the diameters of a new species of apple have a bell-shaped distribution or a normal distribution with a mean of 7.2 and a standard deviation of 0.38. All right, so using the empirical rule, what percentage of the apples have diameters that are less than 6.44? All right, so put your mean in the middle and then start adding or subtracting. I'm going to fill in the left-hand side first since that's the number that I was looking for, 6.44. So that's less than the mean. So I'm filling in the left-hand side first. It really doesn't matter which side you fill in first. All right, so if I subtract 0.38, that gives me 6.82. Subtract it again. All right, so I'm sure y'all are all following, but I just want to make sure. So we subtracted 0.38. Yeah. Then subtracted it again. Subtract it again to get, oh gosh. All right, to get over there. Oh my goodness. Y'all, I'm struggling. I keep hitting the button unintentionally. There we go. Okay. Now I'm going to go the other direction to the right just to be consistent and have my normal curve entirely filled in each time. So I'm going to add 0.38, add 0.38 again, add 0.38 again. So I've got my entire normal curve filled out. Now I'm going to go in here, draw a line at 6.44 since that was the number in question. That was the number that was in the problem. And this is apples that have diameters that are less than 6.44. That would be everything that's lower than 6.44. So everything to the left of 6.44. All right, and now I'm going to refer to my diagram. All right, so 2 standard deviations to the left. So here's my mean, 1 standard deviation to the left, 2 standard deviations to the left. All right, so 2.35, that's this chunk. 2.35. 2.35 is that chunk. And do y'all remember what we said this little chunk on the end is? 0.15, right? All right, so that is left out of the picture. All right, so add those up. What's 2.35 plus 0.15? 2.5. All right, another way you can calculate that is you can say, okay, well, the entire thing was 50%. All right, and you see the arrow on the end. That indicates it goes on forever. All right, so the entire thing was 50%. I can subtract off these 2 chunks, and that'll tell me what's left over here. All right, so that was the approach that I took here, just to show you different ways that you could calculate it. You'll get to the same answer. All right, so if you wanted to take that approach and say, okay, well, I know exactly half of the distribution is to the left of the mean, I can subtract off the 34 and the 13.5, and that'll tell me what's left in the to the left of that standard deviation. So we would say approximately 2.5% of all apples have diameters that are less than 6.44 centimeters. All right, and then last question. Suppose that diastolic blood pressure readings of adult males have a bell-shaped distribution with a mean of 82. That means millimeters of something. Hold on, I'll Google it real quick. Millimeters of mercury. If you're a chemistry major, maybe you already knew that. All right, that's millimeters of mercury. That's our bottom number for our blood pressure reading, like 120/80. All right, so the mean for adult males is 82 and standard deviation is 10. All right, so put 82 in the middle. It says, using the empirical rule, what percentage of adult males have diastolic blood pressure readings that are at least, what does at least mean? If I tell you I got at least $20 in my pocket, I got 20 or more, right? So that's going to be 92 or more. All right, so at least 92 millimeters of mercury. All right, so let's label our normal curve. This is easy because we're just counting up by tens. So 82, 92, 102, 112, and then going down, that would be 72, 62, 52. All right, so draw your line at 92, the number in question. We said that at least 92 means 92 or more, so we're shading to the right. All right, now we're going to refer back to our empirical rule picture. All right, so again, if I'm looking at these chunks over here, you can approach it either way. You can say, okay, this chunk here, let's see, that's one standard deviation over. So that first chunk is 13.5%. Then the next one is 2.35. Then the last one is 0.15. Then you can add those up. The other approach is you can say, okay, well, that's really just 50% minus that first little purple chunk. All right, so that would be 16%. So you'll get the same thing if you add these up. 13.5 plus 2.35 plus 0.15 is going to also give you 16. All right, so we would say approximately 16% of adult males have diastolic blood pressure readings that are at least 92 millimeters of mercury. Okay. All right. Hopefully that gets you started on the homework. If you do have any questions, I hope you will let me know. And I will see you guys in the next video.